In this video, we're going to look at Parkinson's a little bit differently as a terrain problem. So someone you love starts to move a little slower. Their handwriting gets smaller. One hand develops a faint tremor, even when it's resting in their lap. And eventually a doctor says the word Parkinson's. And almost immediately, the entire conversation narrows down to a single molecule, dopamine. The story becomes simple. Your brain isn't making enough dopamine, so we replace it. And that helps for a while, but here's the question almost no one stops to ask. Why did those dopamine neurons start dying in the first place? Because a neuron doesn't just decide to fail. It fails inside of an environment. So what if Parkinson's isn't only a dopamine problem, but a terrain problem? A slow breakdown of the conditions those neurons need to survive. Now, the standard model isn't wrong. It's just incomplete. Parkinson's involves the loss of dopamine-producing neurons inside a region of the brain called the substantia nigra. Replace dopamine and movement improves. That's real, that matters, and I want to be clear about something. Parkinson's is a serious neurological disease with genetic and environmental causes. And nothing I'm about to say is a treatment or a cure. If you or someone you love is facing this, proper medical care comes first. But if the whole story were simply not enough dopamine, then you'd expect replacing dopamine would stop the disease. It doesn't. The neurons keep dying, the disease keeps progressing, and that tells us something important. The dopamine storage isn't the beginning of the story. It's a symptom of something happening further upstream. So picture a garden where the plants are wilting. You could focus entirely on the plants themselves, prop them up, tie them up to stakes, or you could even ask a deeper question. What happened to the soil? Is water reaching the roots? Are the nutrients still there? Has the ground turned toxic? Didn't wilt in isolation. It wilted inside its environment. Your neurons are exactly the same way. They live in a terrain, a chemical, electrical, and fluid environment. And when that terrain breaks down, the neurons are the first casualties. Not the cause, the consequence. Here's the thing. Parkinson's doesn't develop in a neutral terrain. It develops in a very specific kind of environment. And researchers keep describing it with the same handful of words. Mitochondrial dysfunction, oxidative stress, inflammation, and impaired protein clearance. So let me unpack those because they aren't really separate problems. They're one problem. They're one problem feeding itself. Start with the mitochondria, the tiny engines inside every neuron that produce energy. Those engines run efficiently. They leak damaging molecules called free radicals. That's oxidative stress. And oxidative stress does something specific. It damages proteins. And there's one protein that matters enormously here. It's called alpha-synuclein. In healthy brain, it folds into a precise shape and does its job. In Parkinson's, it misfolds, it collapses into a clumped, sticky form, and it accumulates into the deposits we find in Parkinson's brain. But stay with me because this next part is the whole point. Alpha-synuclein doesn't misfold in a vacuum. Proteins fold according to the environment around them. And when that environment turns acidic, oxidized, or starved of energy, misfolding becomes far more likely. Then those misfolded clumps stress the mitochondria even more. So terrain begins to feed on itself. Bad energy leads to damage. Damage leads to misfolding. Misfolding leads to worse energy. It's a spiral and it turns downward. So where does carbon dioxide come into any of this? And I want to be careful here because CO2 is not a Parkinson's treatment, and it has never been shown to reverse the disease. But the real question is, what maintains the environment those neurons live in? Then CO2 genuinely becomes interesting because it works on that terrain at 3 different levels. The first level is flow outside of the cell. CO2 is one of the most powerful regulators of blood flow in the brain. It widens blood vessels, and through something called the Bohr effect, it helps oxygen actually leave the bloodstream and enter the tissue. It's not the same thing as oxygen in the neuron. CO2 helps make that handoff happen. The second level is deeper. It's buffering right at the boundary of the cell. CO2 is the foundation of the bicarbonate system, main tool for controlling pH. And this isn't just about blood chemistry. Mitochondria don't simply burn fuel, they run on gradients. Tiny, precise differences in charge and acidity across a membrane. Buffering is what keeps those gradients stable. It helps hold the exact chemical conditions that let energy production keep running. And there's the third level, the protein level itself. In my book, The Carbonated Body, I go into how carbon dioxide binds gently to proteins and helps preserve their shape and their delicate layer of structured water that forms around the proteins. Now, structured water is still debated science, so I'll say it carefully, but the principle underneath it is solid. Proteins hold their shape because of the environment around them, and carbon dioxide helps shape that environment. There's even early research hinting that CO2 may signal the body to build new mitochondria, the very same adaptation that is triggered during exercise. And there's one more piece of this, cleanup. The brain has its own waste removal system. It's called the glymphatic system. And it flushes out debris, including misfolded proteins, mostly while you sleep. It's driven by your breath and your blood flow. But when breathing becomes shallow and chronic and the CO2 chemistry gets thrown off, that flushing slows down. And the waste that should be cleared away lingers. In a terrain that's already struggling to keep its proteins folded, that is the last thing that neurons need. So maybe the most important question in Parkinson's isn't which molecule failed. Maybe it's this: what happened to the environment that let all of those molecules work together in the first place? And this is why the therapies that seem to help the most, exercise, certain metabolic approaches, aren't really replacing dopamine at all. They're changing the environment. They're improving the conditions around the neuron. Dopamine is the last domino to fall, not the first. The dopamine neuron doesn't die in isolation. It dies inside an environment of failing energy, rising oxidative stress, and collapsing blood flow. And carbon dioxide is quietly one of the signals that helps hold that environment together. Not a cure, not a replacement, a condition of terrain in which healthy neurons always meant to live.